Good afternoon. My name is Jason DeTiberis, and I'm your track host today. If you can, if you're sitting near the edge of a row, please move in so that as folks come in, they have a chance to sit down. And also, please remember to rate this talk on sketch.com at the end. Our next speakers are going to tell us about how container networking affects database performance. First, we have co-author of High-Performance MySQL. He's also the co-founder and CTO of Percona, Vadim. We also have the product manager in charge of MySQL and cloud initiatives at Percona, Tyler Duzan. Yeah.
Cool. So yeah, thank you for the introduction. So we're going to be talking about how container networking affects database performance in Kubernetes. But before we get into that, I want to tell you who Percona is, since we're relatively new to the Kubernetes community. So Percona is a group of open source database experts. We are the unbiased champions of open source databases, and we do services and software around Postgres, Mongo, and MySQL. And all of our software is 100% free and open source. So our commercial business is based on support and consulting services. And then I'm going to skip our little intro since we had a nice intro and talk about why we're doing this talk. So we started kind of entering into the Kubernetes space because we want to be able to make a bridge for databases into the containerized world. You know, historically containerized systems were really focused on stateless applications, not stateful. And so we wanted to move from a place where it's like a don't do this kind of recommendation to, hey, this is a possible thing to do and we should do this in production. So this talk is not about blaming or finger pointing. We are doing benchmarking and showing results, but our focus is really to start a conversation in the community and understand how our adventure started with databases and then how that caused us to get into other underlying primitives like networking and storage in Kubernetes. So a little background on this is we launched our Kubernetes operators for Percona XtraDB Cluster, which is our MySQL clustering product based on Galera, and for Percona Served for MongoDB as GA software in May of this year at our conference, Percona Live. And since then, we've worked with several customers of ours in deploying this into production workloads. And in the process, we noticed really significant performance differentials that we didn't expect. And so the other thing we've seen is that performance can really be a barrier of entry to adoption because a lot of people right now are running Kubernetes for their applications, but their databases still live outside of Kubernetes on bare metal. And so we wanted to understand basically how does the performance differential sit? What are some things that are available in the ecosystem? What are the right recommendations we can make to our customers to make it possible for them to migrate their data into Kubernetes? And part of that ties into storage, part of it ties into networking, and today we're going to focus on the networking piece. And so with that, I'll hand it over to Vadim to talk about our methodology for benchmarking.
Yes, yeah. Hello, everybody. So I'm a performance guy. I like to run a lot of benchmarks. And for this specific case, we had to design our specific benchmark. And first, let's talk about our hardware layout. So for our benchmark, we used 4 nodes Kubernetes cluster with 1 master and 3 nodes. And for internal communication, we use 10 gigabit network cards and network switch. And for external communication with the outside world, it was 1 gigabyte switch. And it seems this setup already caused some complication for several network plugins. We had issue like some of them didn't know how to route network properly. Seems they mixed up 10 gigabit and 1 gigabit connections. So we had to deal with that. And some of them, I don't think we resolved properly yet. Yet you will see that in results. Maybe we can improve our results if we can resolve network issue we had. And for client workload, client generation workload, we use Sysbench, which also was connected on separate box to 10 gigabit network. And let's talk a little bit about database setup. For a database, we use Percona XDB cluster, which again, as product, may be not very familiar for this audience. So I wanted to talk a minute and talk about what a Percona XDB cluster. And basically, if you're familiar with MySQL, and well, if you're interested in that databases, I'm sure you're familiar with MySQL. Percona XDB cluster is basically multiple MySQL nodes communicating together using some synchronous protocol. For this setup, and the minimal recommended way to use is 3 nodes. Just in case there is node failure, you still have 2 nodes running, and if you have only 2 nodes, there are always a split brain situation, which is not good to have. So 3 nodes, minimal recommended setup, and just MySQL nodes running together through synchronous protocol. And this setup allows us to achieve 2 important qualities for databases. What we would like from databases, like high availability and data consistency. Data consistency is achieved by this synchronous interaction between nodes. And this synchronous interaction between nodes happens on the internal communication, which happens through network between nodes. So it would, by itself, it would require and demand a high-performance network, well, if you would like to achieve high-performance results. And the both characteristic from network latency is important, because transaction latency in databases is basically how quickly your application responds to your query. When you run some query, refresh Facebook page, you expect an answer pretty much within a second. So latency, network latency in this case will contribute to transactional latency and to user experience. And also important throughput, because it's not only one user you worry about in high performance workload, hundreds, thousands transactions running per second. And in this case, transactional throughput will depend on your network throughput. So this setup applies quite demand on network performance. Another aspect of databases is storage, and especially if you use shared storage, which running across network, there is additional demand of network. But in our setup, we will leave storage out of equation just to understand networking aspect of database performance. And for a database layout setup, it would be very simple. 3 nodes of Percona XDB cluster. For this, we allocate each node would run in an individual pod as used in our operator, and then we prescribe anti-affinity rules in our operator. So we guarantee that each node will run on individual bare metal server. So this kind of mapping of Kubernetes pod running, we guarantee that each individual pod runs on a separate server. And we use client Sysbench outside of this network, outside of Kubernetes, using port mapping to access databases. So for benchmarking by itself, we used on the software side, we use Sysbench with OLTP read-write workload. It's a very simple workload, but it allows to load database pretty decently. And read-write would allow us to load network communication between nodes, where network communication happens when there is changes. There is a write workload to database. And along with this, we'll measure just raw network bandwidth, which we're able to achieve with some or another plugin. And for this, I used iPerf3, a very simple tool to capture network throughput. We also collected for baseline, we collected results on bare metal, on system running without Kubernetes, so that we understand what is kind of ideal performance we would like to achieve. And compare Kubernetes operation with the bare metal performance. Network side, like I mentioned, we use two network cards, one 10 gigabits, another 1 gigabit for communication between nodes, and operation system a little bit outdated, but that's what we had on the system. Ubuntu 16.04 with 4.15 Linux kernel. Then Kubernetes, to deploy Kubernetes, I used very simple kube admin script, which would allow us to spin up 3 nodes and 1 master. And then we installed network plugins. Probably Tyler will speak about it more. And we did our best to configure a network plugin to use 10 gigabit network interface. Like I mentioned, I don't think we were successful in all cases. It required some extra work. For hardware, well, the hardware specification of our servers, I will not list it. I think that's pretty decent Intel machine with enough memory and decent storage options. And on software side, we use the Percona XLB cluster 5727. Our nothing special, using our system packages from our repos. For Kubernetes tests, we used our operator version 1.2, which would deploy the same version of Percona XLB cluster in Kubernetes 5727. And but to achieve better database performance, we cannot rely on out-of-box parameters yet. We still have to tune configuration like myCNF in cases with MySQL. And we used local storage, local SSD storage, again, to avoid this shared storage case which would introduce additional workload on a network. We would like to isolate storage problem from network problem in this case. So there is some basic parameters if you would like to repeat. And actually, very first issue I faced here trying to measure database performance is quality of service in Kubernetes, which by default is best effort. But I will show on next slide. If you use the default quality of service in Kubernetes, your result variance will be, first results will be suboptimal, and second variance in results also will be quite problematic. So it also took time to figure out what's going on here, and then we came to the need of using guaranteed quality of service, and actually to make sure that you're using guaranteed quality of service for Kubernetes pods, you have to specify this kind of magic parameters, request and limits to be exactly the same and as high as possible for your pods. Then your pod in Kubernetes will provide best optimal performance. And still I had to use this magic number CPU 55, even there is a 56 cores, including hyper-threading cores. Kubernetes would not allow me to put 56 CPUs here. Kubernetes complaining or lack of resources, so I had to increase on 1 CPU core allocated for our database pods, which also might contribute to some decrease of performance, but I hope not that significant. And and there is to compare guaranteed quality of service which we used with best effort quality of service in Kubernetes, which will run by default. This chart kind of 1 second resolution, and you see with best effort quality of service, you will see a lot of variance and suboptimal performance with this setting. And for the reference, we used the Sysbench OLTP read-write test. With these parameters, 10 tables with 10 million rows each, you will get about 32 gigabytes of data. We have 100 gig of memory, which is much bigger than 32 gig database. So pretty much all our workloads will be done in memory with minimal impact on storage. So again, with goal to load network to see what happens in case when network performance is bounded by network plugins. And on networks plugins, Tyler will talk about network plugins which we use.
Thank you, Vadim. And so as you can see, we're trying to be really transparent about what our methodology is here. We recognize a lot of times when folks do benchmarking, it's hard to replicate them or they're not very transparent. So our goal is to start a conversation in the community and really understand how we can improve performance across the board in Kubernetes for stateful applications. And so I'm just going to give a quick overview of what the network plugins are that we tested and maybe some notes that we took on these, but no strong recommendations or conclusions. So also, I was going to say the list of plugins we tested is not exhaustive. We chose the ones that we heard about from our customer base. So if customers were using them or had considered using them, they got added to the list. So I already found like 3 more at the conference this week that I hadn't even heard of yet. So we may be testing more in the future. So first up, we tested Calico, which is described on their website as Project Calico is designed to simplify scale and secure cloud networks. And one of the interesting things is it supports an IP and IP feature. So we tested with and without, and it's enabled by default. We tested Flannel. Flannel is described on their website as a network fabric for containers designed for Kubernetes. And it has support for actually multiple backends. The ones we tested was the default UDP, and we also tested VXLAN. We attempted to test host gateway, and we saw some interesting behavior, and then ultimately were unable to complete a test successfully, so we removed those results. But we were able to see pretty good, on average, performance with VXLAN. But interestingly, with VXLAN, we saw weird stalls. So peak performance was good, but we had not very good consistency. And we think that might be a kernel issue because of the age of the kernel we were running. We were on 4.15. So we're going to look at that in the future. But since all tests were run on the same hardware, it's still a valid set of results. We also tested Cilium. Cilium's described on their website as API-aware networking and security. We found the installation of this very straightforward, but we were unable to get Cilium to actually route traffic across a 10 gig network as we expected. So we are reporting results for Cilium. However, we expect these are heavily impacted by this. Similarly, Weave, which is described on its website as simple, resilient, multi-host container networking and more, was actually probably the easiest to install, but we still had some concerns with trying to get it to route across 10 gig. This was actually a very interesting one where the result was we thought that it was routing across 10 gig, but the performance results didn't match that. And then on further investigation, p-capping, we saw it was going across the gigabit interface, even though the routing rules that we could see showed it should have gone across a 10 gig interface. So we ended up doing really significant troubleshooting on Slack with some folks, and then ran out of time, so we ended up reporting the results that we had, and we'd like to readdress this one also after the conference. We tested Intel's SR-IOV CNI driver alongside Multis, and this is kind of interesting. Multis basically enables you to have multiple CNI drivers used to attach multiple interfaces to a pod. So with this one, we actually used Kube-Router as a default pod network, and then we added an additional interface inside the pod that was the 10 gig interface provided by SR-IOV. And then finally, we tested Kube-Router. And this one was it's described as a turnkey solution for Kubernetes networking. We found that relatively be true. It pretty much worked. You could deploy it directly with KubeADM. And with that, I'm going to hand it back over to Vadim to talk about the results.
Okay. So let's talk about results. First, I measured the database throughput on bare metal. And again, to make sure that network is a limiting factor here, I measured the database performance through a 1 gigabit channel. And in this case, for Sysbench workload, we achieved 2,700 transactions per second. And when I switched to 10 gigabit network, the result improved to over 7,300 transactions per second. Actually, you see the results did not improve quite 10 times as a network characteristic, but we can see that the database performance is clearly limited by 1 gigabit network bandwidth in this case. And on this chart, I trying to summarize the results. It's maybe a lot of data to process, so let's go through this. So this kind of green line is network bandwidth, which I measured with iPerf. And first column is bare metal, and there you can compare different plugins. Actually, the best result for network bandwidth I was able to achieve with SR-IOV, but by some reason, database performance was far from ideal in this case. And we're working with the Intel guys to understand what's going on here. Obviously, there is something going on a database level. But then both Kube-Router and Calico with disabled PIP showed, I would say, comparable network bandwidth results, comparable with bare metal. But then when we switch to database performance, database throughput, it's a red column in my result. So the best performance we were able to achieve with Kube-Router, with Calico being second. As we mentioned, there are some plugins like Cilium, Viv, and Flannel. It clearly shows that by some reason, with these plugins, we directed our traffic through 1 gigabit network interface. And there is still work to figure out how to set up them properly. Well, in any case, it did not work by default, even with some efforts to set up it properly. So, but we are ready to work with network providers to be able to figure out how we can resolve this issue. So, in conclusions of results, we still see some performance penalty using Kubernetes, using database in Kubernetes. Even the best result we have with Kube-Router produces about 13% performance penalty if you compare with running identical setup in bare metal. Some network plugins I mentioned would require extra work to make them working as expected. And you can see there's a strong correlation between available network bandwidth and database results. That obviously network performance very important for database performance.
Okay. With that, we're ready to take questions. And of course, we're always available at the Percona booth for the hallway track if there's interest in that. But let's see if there's any questions in the room, please. Oh, we'll start with Josh here.
Yeah, of course. So in this benchmark, you're using a distributed version of MySQL through XtraDB.
Yeah. That's correct.
Right. Did you try any single node MySQL?
So to clarify, all of the traffic was directed to a single node. So typically in our operator, we deploy a 3-member PXC cluster with 3 members and a proxy SQL cluster in front of that routing traffic. And we do that for resiliency because of some deficiencies that exist in stateful set for the purpose of MySQL. So this is kind of a crutch we use around it. But for the purpose of the benchmark, we eliminated proxy SQL, so there was no proxying layer, and we targeted all of the traffic to a particular instance of MySQL running in the cluster.
Right, but it's still replicating, right?
That's correct, and we did that intentionally because in the case of running MySQL for production purposes in Kubernetes, you need synchronous replication to have some of the guarantees around reliability and resiliency. So it would be a less effective test, in our opinion, for our purposes if we were to do single instance.
Yeah, I was just checking because the overhead you were seeing was consistent with the overhead that I had for distributed databases, but not for pure single node.
Yes,
and that makes sense because you effectively distributed data anyway.
Yeah, and that's absolutely correct. So because it is synchronous replication, at least for write workloads, any latency the network layer adds acts as like a multiplying factor because of the synchronous replication. Yes, this gentleman here. Oh, please wait for the microphone so that it gets on the video.
Have you tried running the same benchmark with something like Aurora?
So we have run similar benchmarks in the past with Aurora, but it wasn't really in the scope of what we were trying to discover here. So this isn't intended to be comparative to other types of database deployments in the cloud space. This is really focused on customers that are considering moving from bare metal to Kubernetes. We think, in our opinion, we agree with what Sugu said the other day in his keynote, that to gain the agility of Kubernetes, you need your data in Kubernetes too. And part of what we're doing at Percona is trying to do this in a really community-driven, open-source way so that everybody can get their data into Kubernetes and it be production-ready. But part of that is to address the barriers of entry like performance. So we were very specifically focused on bare metal to Kubernetes. We did not do any comparative analysis. But we have done separately benchmarked Aurora, and it's on our blog if you're interested. This gentleman here, and then this gentleman.
Did you guys consider the impact of storage?
So not for this. So we very specifically isolated storage away. It is true that storage is also important for database performance, but we want to make sure that we're making effective and valid benchmarks. So for benchmarking networking, we intentionally set up a workload in a scenario where there would not be any real storage aspect to the performance that was delivered.
Hello. Had you considered chaining together multiple CNIs? Because it looked like one of them was better at mounting both of the NICs, and possibly chaining another one after that could, kind of reap the benefits of both.
Yeah, it's not something we had in scope, but it's something we're interested in considering. And if you want to talk after, I'd be happy to have a discussion about that.
Yeah, Josh, go ahead.
Oh, this gentleman actually over here in the blue. Oh, sure. Yeah, and then this gentleman in the blue.
If you want to see a comparison of benchmarking across different storage types, check video from the last two KubeCons, Barcelona, from Barcelona and Seattle. Various people have had presentations about that, including me.
Okay, and this gentleman in the blue over here, I think, was next. Sorry, please wait for the microphone.
So I see on one of your figures you measured the network throughput. Have you also measured the point-to-point network latency? And
yeah, so latency.
Network latency was not measured.
Yeah, it wasn't really measured as part of this. I mean, iPerf does give some results, but we were looking at throughput primarily. Obviously, latency has an impact on throughput once you get to database workloads. So it's part of something we'd like to expand on here. But the way that we reported the results right now is it's associated to throughput out of iPerf for pod to pod. This gentleman here, and then this gentleman here.
Hi, how are your benchmarking nodes talking to your main database? Was it a node port, and then internally for node communication, was that pod IP to pod IP, or was there any kube proxy service IPs going on in there?
So client talks to nodes through node port, and the internally pods communicated through network.
Yeah, through the pod network that was deployed.
Pod network.
Yeah, we didn't use any kube proxy in there.
So maybe it's a similar question, but how did you make sure that the iPerf numbers were using the exact same networking paths as the database was using in in its operations?
Okay, so essentially, because the 10 gig and 1 gig network interfaces on the host were on completely separate layer 2 environments, and all of the internal communication based on the configuration of the database was going across the interfaces provided on the 10 gig. And in most cases, the only real case where we had to explicitly do that was with SR-IOV because it provided 2 interfaces. All of the other network plugins basically provided the pod network, and the pod network was on 10 gig, so there was no other path. But with SR-IOV, we explicitly configured the database to go across the 10 gig interface. So I think that answers your question.
Hi, can you comment on the variability in the graph with all the results?
I'm sorry, can you repeat?
The variability of the results.
The variability of the results?
Yes.
What about the variability?
Whether in bare metal you had more noise or variability than the others.
This one?
Yes.
I'm not sure I understand the question. Can you repeat?
Like the standard deviation of the results, if you had.
Okay, no. So we don't have that in a reportable format right now, but yes, we have all of the results collected in a spreadsheet. I apologize, that wasn't reported in here, and I can't say off the top of my head.
So typically, well, let me comment on that. Typically, when I measure database results, unless it's a very specific environment, I want to see that results very stable, that's very minimal variability. The only issue we had, like Tyler mentioned, with Flannel VXNet plugin, that we observed some stalls in database results. Like it was stable results, then was dropped to 0 for a couple of seconds, then again a stable result. So that's only issue with the variability we observed in this setup.
All right, any other questions? If not, then please feel free to reach out to us by going to our booth in the expo hall area, or just find one of us in the hallway and we're happy to talk.
Thank you.